Okay, so there's a follow-up video. It's the beginning of 14.7 on filters, but really, if I were in class, I'd be making many more examples of Bode plots without giving you the transfer function. So this is what I'm going to do here, 2 examples of how to quickly come up with a Bode plot without having to really sum up all the individual functions. Of course, you can continue to watch those videos on the how to make a really nice Bode plot. This is a job interview question again. It's like, I will give you the gain, 0 and a pole, draw the Bode plot without thinking too much. So let's remember that a 0 makes the Bode plot go up, so the gain for omega tending to infinity will be super high. So zeros are very tricky when you actually design circuits, so be careful, because with high frequencies you have super high gain. You usually saturate your amplifiers or your speakers if that's a sound system. And then poles make it go down. So no matter which amplification you have early on, if you have a pole, you know that it's going to be a low-pass filter. So this connects to filters, because usually in a Bode plot, if you draw something like this, this is a low-pass filter because there's a high gain, or whatever gain there is. Let's say even a gain of 10 here, 20 dB gain at a corner frequency, omega C for, we're going to see this for an RC circuit. You start going down with the gain, so for very high frequencies, there is no gain. So this passes all these frequencies up until the corner frequency. And a high-pass filter, the same thing, so except any frequency above the corner frequency, you have a reasonably high gain, or whatever gain you want, for example, 100. And then for low frequencies, you're cutting them off, so the gain goes very low. And I'll put, for example, I'll put here minus 40, which is a 10 milli gain times 0.01, where you divide the signal by 100. So this is a low-pass filter. This is a high-pass filter. If you combine those two, obviously you have the other 2 kinds that we're going to see next class, which is a band pass. So you're only passing these frequencies here from a low to high, or a band reject, which is you have high gains for everything here, but between the low and high, you have very low gain. This is typical. The most used one that you may be asked to design is a notch filter, which takes out, for example, 60 hertz, or in Europe it's 50 hertz. So we, as I was designing systems in Germany, we made notch filters for 50 hertz. So these are Bode plots for filters, but really I want to make sure you have a feeling for how to draw this. So a gain of 10 is 20 dB. So for this Bode plot here, without knowing the transfer function, I would like you to have a feeling on how to draw it. If you have a 0 at 10, what happens is you had 20 anyway, and at 10, you're going to start increasing 10 times each decade, which is 20 dB per decade. So this is the Bode plot goes up. And now the pole is only at 1,000, so this 0 is still active. Still making my system go up between 100 and 1,000 radians per second. And then at 1,000, when I have the gain at 60, the pole starts being active, which means it goes down 20 dB from what it was doing. So this is the graph of this Bode plot, of this 1, 0, and 1 pole. So this is going plus 20 dB per decade. Also, if I give you this Bode plot, you should be able to tell me what the transfer function is. And now let's do the second one. A gain of 10 milli. Someone asked me what 10 milli was, or 1 milli. It's 10 to the minus 2, or it's a gain of 0.01, which is minus 40 dB. So this, instead of 0, I'm considering the minus 40 dB. So I'm going to think of my Bode plot more or less around 40. And now I go to the lowest number here. So instead of 100, here obviously the 0 was at 10. It was convenient. The pole was at 1,000. But here I have a pole at 1, then a pole at 10, then a 0 at 100. So I'm going to go with 1 is the first number here. This pole at 1 means that it was minus 40. It's going to start going minus 10 times per decade, which is minus 20 per decade. But then when it gets to 10, there's a second pole. So instead of minus 20, it's going to go minus 40 per decade. Or it's going to be 100 times smaller. Every time I increase this frequency by 10. So this is until 100. Am I right? No. Yes, from 10 to 100. Yes, the reason I went to 100 is because at 100 I have a 0. So what happens here is that this is my A section, B, and then I'm gonna do a C in a second. So A is minus 20 dB per decade. B is going at the minus 40 every decade. Oh, I meant to take my hand off. And then at 100, I finally have a 0, which makes my Bode plot go back to minus 20 per decade. So from minus 100, now I'm going to only go to minus 120. And at 10,000 radians per second, I would get to minus 140 dB. I don't know if you can see there. So this is supposed to be a straight line. Need to go back to elementary school to draw. So my C phase there is again minus 20 dB per decade. And it keeps going down. So really these higher frequencies here will never get amplified. Of course, the whole thing was not amplified anyway, so you're just putting a 0.01 gain until 1 radians per second. After that, it's really, there's no signal at all. So I really want to look at Bode plots from the perspective of amplifying different kinds of frequencies. And this connects really well with filtering because all there is to filter is understanding the magnitude. Well, sometimes you're worried with phase too. We can talk about this later in class. I mean, in this course. But the basic idea of a filter is that you manipulate the gains for different frequencies by doing RC circuits, RLC circuits, and taking the signal either on the resistor or the capacitor, inductor, or combinations of those. So I hope this is clear on how to put together a Bode plots just by looking where your zeros and poles are. And this is relevant for several different areas of electrical engineering.